Thank you so much. It's a real pleasure to be here, and I'm so delighted to have people to speak to. It's a tradition after you receive the Nobel Prize to give a lot of talks. So for the last year, I have given a lot of Zoom talks, so to that green dot at the top of my screen. So it is wonderful to be able to speak to people who have three-dimensional shapes. Yay! And thank you for coming out tonight. So it's a pleasure to share the work that I've been doing for the past 25 years that was recognized. I started this program when I first became a professor at UCLA. I was incredibly excited to have the privilege to use the Keck Telescopes. These telescopes are co-owned by the University of California and Caltech, and they are the largest optical and infrared telescopes in the world. And they had just opened at this time. So this to me was my dream job. And I was very excited about using this telescope in new and different ways to study black holes. And as Stein has already shared, I did start with a small, lean, and mean team. I really want to give lots of credit to the people that I've worked with over this time period. On the left are Mark Morris and Eric Becklin, who I've worked with for 25 years. I'm in the middle, quite a bit younger. And then my first graduate student ever. This is at a time when we first put in the proposal, when people actually said no. The very first proposal was in 1994. And people didn't believe that our technology would work. They didn't believe that we could find the stars that we needed to find, and they didn't believe that the approach we were proposing for doing the science would work. So it was a lot of no's, but no is an interesting word. I am a firm believer today that every challenge is an opportunity. You just have to look more closely. So in my case, I had to understand that I was low man on the totem pole. I was first-year professor. I had absolutely no credibility in the system to use this fabulous facility. So it was really my job over that first year to convince people, the august, what we call the time allocation committee. Every night of this telescope is allocated through a process that happens every 6 months. Every night is precious. The value of a night in terms of the operational budget is roughly $100,000. So this is really a precious, precious resource, and it's very hard to come by. So you have to work for it. And there were a lot of good scientific reasons as well as technical reasons why people were skeptical, and I'll try to share some of those reasons as we go along. Today, we're a much bigger group. The group is roughly two dozen people. And I'm really delighted to share that not only are Mark and Eric still members of the team, but we have some really important core members who are part of the conference today. So on the far left is Jessica Liu. She gave a talk on the very first day of the conference that we're having out at the Aspen Center for Physics, and then Tuan Do. These two started in the group as grad students. Today they're professors in their own right with their own grad students. So it's been a wonderful 2 decades of expanding not only the science that we can do, but the team that's involved. Okay, so we've also gone from being a very small team begging for telescope time to a team that's referred to as a key science project team. In other words, we now have responsibility for justifying or arguing why this facility should be expanded. So it's a very different relationship that we have with this facility compared to where we were at the beginning. So there are let's focus on the science now. The question that I posed in the beginning was, is there a supermassive black hole at the center of our galaxy? And what I hope to convince you is that the answer is resoundingly yes, and that we have a wonderful opportunity now to study not only the physics, but the astrophysics of these supermassive black holes. And I really want you to keep this in mind, that there are 2 very different big picture perspectives on why this is an interesting question or effort to pursue. From a pure physics perspective, we want to demonstrate that these objects really do exist in the universe. There's some fundamental physics reasons why one might be skeptical We don't have the physics today to explain what a black hole is, because a black hole, as I'll get to, forces an inconsistency or a lack of ability to communicate or connect two fundamental fields, and I'll get to that in a second. So that's a physics perspective on why this is interesting. And then from an astronomy, astrophysics perspective, we are interested in understanding what role these very massive exotic objects play in the formation and evolution of galaxies. And galaxies are the building blocks, the fundamental building blocks of the universe. And today, we think that there's a very important feedback mechanism between the two. In fact, when we first started to report the results that there is a black hole, people used to ask, well, which came first, the black hole or the galaxy? It's kind of like a chicken or the egg question, which came first? And as scientists, we're really good at coming up with explanations. We had explanations that explained both. And it turns out we were asking the wrong question. And the reason we think that we were asking the wrong question is because today we understand that the mass of black holes seems to correlate with the mass of the central component of these galaxies, suggesting that there's a fundamental relationship and that whatever formed the black hole had to synergistically form the galaxy, and that there's a constant feedback mechanism between the two. In other words, they had to form together. Okay, so those are the two big picture perspectives. Oh, and actually during the cafe, something else occurred to me in terms of one of the discussion that was going on. People often ask, well, what's the difference between physics, astronomy, and astrophysics? Well, I'll tell you my version of it. If you get on a plane and you don't want to talk to the guy next to you, you say you study physics, because it's going to end the conversation. If you want a really long conversation, you tell them you study astronomy. And if you want a mid-scale conversation, you say astrophysics. So that's my definition of the difference between the two. That's right. They're all very interconnected and share a huge commonality in terms of the fundamental science that goes into these things. Okay, so how do you observe something you can't see? That's a fundamental question when you want to find and study black holes, because black holes are objects whose pull of gravity is so intense that nothing can escape it, not even light. So we can't see it directly. So let's start with a definition of what a black hole is. It always seems appropriate to put up a totally blank slide for a couple of reasons. A black hole is an object whose mass is confined to 0 volume. Okay, so if we think about mass divided by volume, and that's density, density goes to infinity. And in physics, anytime a number goes to infinity, we call it a singularity. And I like to call it, it's like a big, giant red arrow that says, you do not have your description of the physical world right here. Okay. So black holes are really interesting to physicists because it really points the direction to furthering our understanding of fundamental physics. Black holes are objects where gravity wins. Gravity wins over all other known forces. And in fact, so this is the problem. We don't know how to make quantum mechanics work together with the field of general relativity, which is what Einstein's so famous for. So when we figure out how to make these two fields work together, presumably we'll know what a black hole is. So far, I want you to conceptualize these black holes in that simple way. The mass is confined to 0 volume, so they're infinitesimally small objects. And there's a very special size that you can associate with these objects. So remember, the physical size is infinitesimally small, but there is an abstract size that we can associate with them. It's called the Schwarzschild radius, after the guy who understood the importance of this radius. It's also known, it's been popularized as the event horizon by Star Trek. It's the last point at which light can escape from the black hole. Okay, so you can't communicate over this event horizon. So outside, you can't see with, beyond that event horizon scale. It's important also because every object has a Schwarzschild radius associated with it. You do, your neighbor does, your cell phone does. It's really simple. It's a number times your mass. The bigger the mass, the bigger the short shield radius. And all you have to do is get that mass down to this scale, and then gravity overcomes all other known forces and forces the object to become that infinitesimally small object known as the black hole. So this is the radius at which gravity wins. So in a sense, demonstrating the existence of a supermassive black hole really boils down to showing that there's a lot of mass inside a very small volume, and ideally down to the short shield radius. So let's look at what the scales might be. So if we could take the Earth and scale it down to the size of a sugar cube, it would become a black hole. It's been pointed out to me that the younger generation probably doesn't know what a sugar cube is, and it probably need a better analogy, so let's say a penny. Okay, now, as I said, the short shield radius just scales with mass. So if we took the sun and shrunk it down to the scale of UCLA, I had to put UCLA, I'm from UCLA, it would become a black hole. Okay, so now hopefully we have the concept of what a black hole is and really conceptually what we're after in demonstrating the existence of a black hole. We want to show there's a lot of mass inside a small volume. Next, I want to get to, I've been saying supermassive black holes are what I study. So why do we say supermassive, and what does that mean? It's really getting at, in astronomy, we talk about two types of black holes. And they're different in terms of mass, but they're also different in terms of how we arrived at our conclusion that they existed. The first kind, which I'm going to call the ordinary black holes, as if there could be such a thing as that we would label as ordinary, as a black hole. These are objects that we understood from a theoretical perspective in the beginning. In other words, people did the thought experiment of how do massive stars in our galaxy evolve, spend their lives, and end their lives. And the conclusion from a theoretical point of view, so fundamental physics, is that these very massive stars that are roughly 30 times the mass of our sun or larger explode. So that's what we're looking at here, is the explosion. This is a supernova. So the outer layers go shooting off into the universe, and all sorts of really important things happen in this explosion. It's actually how we fundamentally get from very simple elements to the chemical richness that we have and really expect here on Earth. But what I care about is in the middle. The middle layers actually have the conditions such that gravity wins and overcomes all other known forces, and there's a little black hole that's created in the center of this object. Okay, it's thought that generally these are roughly 10 times the mass of the sun and larger. So ordinary black holes thought of from theory, roughly 10 times the mass of the sun. Now this was confirmed with observations beautifully, with observations of binary stars or pairs of stars. And then recently really demonstrated exquisitely with the measurement of gravitational waves. It was a beautiful confirmation of the existence of the stellar mass or the ordinary black holes. Now the ones that I want to share with you this evening are the supermassive black holes. So rather than being 10 times the mass of the sun, or slightly larger, these are 1,000,000 to 1,000,000,000 times the mass of the sun, and hence the word supermassive. They're really big. Okay, so the story here is quite different, because rather than starting with theory, the story starts with observations, and observations of galaxies. So there's this picture that we're looking at here is a wonderful depiction of galaxies. So every object that you see in this picture, I don't see except one, the one with the crosshairs, that's a star in our galaxy. But everything else, sorry, that's a star within our own galaxy, and everything else is a galaxy. So roughly 100 billion stars in each one of these things. Let's maybe turn our attention to the top left. You can see that spiral galaxy. That looks like our own. That's what our own galaxy would look like if we could get outside and look back. Okay, and I'm going to come back to that guy in a second. But what is the observation that made us think about the existence of supermassive black holes? There's nothing in this picture that made us think about that. I just wanted to demonstrate the scale of galaxies. Okay, so before we were looking at one star, and now we're looking at many galaxies. This is a picture that was taken with Hubble Space Telescope at wavelengths that are what your eye detects, so an optical or visible wavelengths. This next picture is a picture of a single galaxy, and it's taken at radio wavelengths. And it shows an example of a special kind of galaxy. It's called active galactic nuclei because their nuclei, their centers, are very active. And the scale of the galaxy, all the stars, are around that bright central spot in the middle. We don't actually see the starlight, but we see the emission from gas, very energetic gas. And there's two things that are really striking about this, this object. One is that there are these jets that are coming out from them. Okay, and if you just measure how fast these jets are moving, you know that there's a very powerful central engine that's powering these jets, that's spewing out all this gas from the center of the galaxy. So that's what made people think about, well, there has to be an interesting central object in this galaxy. The second thing is that the bright dot in the middle is emission or light that doesn't look like anything that stars or normal gas would emit. And it looks like very hot gas. And it was suggested that perhaps a supermassive black hole could drive all this activity. So you can see that there's a difference here. We're starting with an odd observations, and then we're following up with theory, in contrast to the first case, where we start with theory and follow up with observations. Now, these galaxies, these exotic galaxies, these AGN, active galactic nuclei, I like to call them the prima donnas of the galaxy world. They're kind of show-offs. They're only about 10% of all galaxies. But nonetheless, it got us thinking about supermassive black holes. And roughly, 50 years ago, it was suggested that maybe all galaxies harbor supermassive black holes at their centers, but they're just quiet. They're lurking at the center. Oh yeah, the analogy I like to make here, let's see if I can go back, is that that big red dot in the middle is matter just outside the event horizon. And you can think of, the idea is that you're seeing matter fall through the event horizon. So you're watching this galaxy dine on a lot of matter around the black hole. So the analogy I like to make here is that it's like a Thanksgiving feast that this galaxy, or the supermassive black hole, is having at the center. In normal galaxies, the idea, normal, ordinary, garden variety galaxies, and I have to say, that's where we live in one of those ordinary, nothing special about us galaxies, the Milky Way. So as I said, this is a zoom in to what we were looking at before. The galaxy was that it was at the top left. So if we could get outside our galaxy and look back, this is very much what our galaxy would look like. Galaxies are generally flattened disk-like structures. And in fact, all this structure that we're seeing in the galaxy comes from compression of gas and is lighting up where stars are being formed. Our sun and our solar system lives about halfway out from the center of the galaxy to the edge. And as you go to the center of the galaxy, almost every way that you can describe the galaxy gets more extreme. So to take one important characteristic, if we talk about the density of stars, how crowded the stellar population is, the density of stars goes up by a factor of 1 billion from where we are to the center of the galaxy. So you can think of the center of the galaxy like a dense urban environment where things are really crowded and dense and things move fast. And there are a lot of other characteristics that just get more extreme as you go to the center. So our sun out in the suburbs, things are nice and spread out, things are calm, things are extreme as we move into the center. And the center is where we're looking for a supermassive black hole. All right, so if we want to look for these supermassive black holes, our galaxy is definitely the best place to look because it's the closest center of a galaxy that we'll ever have to study. The next closest galaxy to us is 100 times further. So the pro of studying the center of our own galaxy is proximity. And when you're close to things, you can see in great detail. So that's a pro. Now, like in life, for every pro, you usually get a con. And the con in this case, remember I said that galaxies are flattened disk-like structures. We live halfway out, and we're trying to see towards the center. So this is a photograph taken from the side of the Big Island in Hawaii. And you can see the plane of the galaxy. So all that white stuff, those are the stars that define the plane of the galaxy. But hopefully you'll also notice that there's a lack of light down the middle of that plane. And that comes from all the dust that also resides through the plane of our galaxy and gets more concentrated as you move towards the center of the galaxy. Now, I'm from Los Angeles. I have a great appreciation for dust in the atmosphere. Turns out that the dust in our galaxy has the same properties. They're the same size. And dust is very good at absorbing light that has a wavelength that's roughly the size of the dust particle. So really, really, really good at blocking light that our eyes can detect. So remember we were looking at that Hubble Space Telescope picture? Not going to see the center of the galaxy at these wavelengths, as you can see here. So the key to this work, actually there's a couple of key technical advances. And one of them is the ability to look in the infrared. So light that is just longward of what your eye detects, it's where your TV remote control works, and it has a wavelength that's bigger than most of these dust particles. So you can actually see through all the dust. So you need to be able to go out to the infrared. And this is, that detector technology has been going through a huge explosion roughly at the time when that telescope, Keck, was opening. So in fact, one of the brilliant moves that UCLA made in terms of this collaboration between all the campuses of the University of California and Caltech was to recognize that infrared astronomy was going to be really important to this telescope. And Los Angeles, the Los Angeles area, is jam-packed with the aerospace industry, which cares a lot about this technology, because if you want to do night vision or heat detection, infrared detectors are essential. So it was a really good partnership. So in fact, I was hired at UCLA as part of a overall thrust from UCLA to move into the infrared. So that's where all of this work has been done that I'm sharing with you. Now, we want to show that there's a lot of mass inside a small volume. The most direct way we can do this is to observe or to measure how that black hole, the gravity from that black hole, influences objects around it. So in a sense, it's a very conceptually simple experiment. We want to look at the stars that are as close to the center of the galaxy as possible, and we want to measure their motions. These stars orbit the black hole, if it's there, for the very same reason that planets orbit our sun. It's just gravity. And the orbit, what we need to do is measure how large the orbit is, the radius of the orbit. I mean, this is an oversimplification because things don't all move around in circles. There's ellipticity here. But we measure the radius of the orbit, or what we call the semi-major axis. And then we have to measure the period, how long it takes to go around. Okay. And in the beginning, we weren't even thinking that because that was way too ambitious. We were just saying, well, let's just measure how fast they move, the speeds on the plane of the sky, and that'll take us 3 years. Okay, so okay, so just keep that in mind. We were only proposing a 3-year experiment. Okay, but we want to see the stars that are as close to the center of the galaxy. Oh, I guess I should have said one more thing in this description. Each star is moving under the influence of the mass that's inside its orbit. So you want the stars that are as close to the center of the galaxy as possible. So you're inward bound, you want to be able to discover those stars. So that tells you why I was so interested in Keck. Okay, so Keck, largest telescope in the world, ground or space. Big telescopes effectively have 2 campaign promises. Okay, so the first, which is actually what really dominates the use of this facility, is the idea that the telescope, and it's actually the primary mirror that you can just barely see. You see the support structure through the dome slit, And at the bottom, there's a mirror, and we describe how big telescopes are by the diameter of these mirrors. The Keck is 10 meters in diameter, and to give you a sense, that's like the width of a tennis court. And I'll go ahead and mention that jump in diameter was achieved by building a mirror that was designed with many segments. They're hexagonal segments because hexagons are the shape that can fit most without gaps, and most best approximates a circle. Okay, so you see hexagons a lot in nature. And that's important because you need those segments to be aligned to a fraction of the wavelength you're trying to observe. So that's difficult technology. So we're thinking about the two campaign promises. The first is you just think of the big mirror as like a light bucket. The bigger your mirror, the more light you collect. You can see things that are fainter. In astronomy, that generally means further away. Okay, so that's been a big thrust. But the thing I really care about is the second promise, which is the idea that the larger your telescope, the better your ability to resolve detail. So we call this angular resolution. And the analogy I like to make here is that if you think about the artistic technique or the painting technique of pointillism, where you paint with a bunch of dots, and the closer you stand to the painting, the better your ability to see those individual dots. So you improve your angular resolution by standing closer. So in astronomy, in principle, the larger your telescope, the better your angular resolution. In other words, the better your ability to see details. So I'm going to come back to this in a moment. Actually, I'm just going to go ahead and ask you guys this. We've built this telescope in Hawaii, and there was a lot of discussion, and whenever you build a big ground-based telescope about where to put it, Hawaii turns out to be one of the best places in the world to build telescopes. Do you guys have ideas about why? It's dark. We don't like light, so light pollution, really bad. So Hawaii, get away from city lights. In fact, in Hawaii, if you've ever been to Hawaii, you might notice that the local street lights are very yellow. So they're not like these lights that emit a bunch of different wavelengths. We like the way they look. It's warm light, but it's really a pain for astronomers because you can't notch that contaminating light out. Okay, so it's dark. Dark is number one. Any other ideas? Pardon me? Elevation, yeah, you really want to be very, very high because you want to get through most of the atmosphere. The atmosphere absorbs your light, and it also distorts your light. So the first characteristic is actually why you want to get to a high peak. Any other reasons? Climate, and I'm going to take that in a very specific way. Actually, we don't like rain, because you'll lose your night, so no clouds. And you also want your airflow to be very smooth over your island to keep the atmosphere very still. Whatever is left, you want not still, but very smooth, so what we call a laminar flow. So this means that if you think about the telescopes that are located all around the world, you'll see them on tall peaks near big bodies of water, because big bodies of water create the very smooth airflow. Okay, so I think we've got most of the ideas here. So this is on the top of Mauna Kea. Mauna Kea is up at 14,000 feet. If you've ever tried to, actually, I'm here puffing and puffing because we're up at 8,000 and I am not acclimatized yet. 14,000 feet is a really interesting place to work. Your brain doesn't work very well. Actually, the story I always like to share, and I'll share with you guys tonight, is I remember, actually, it was with the grad student you saw on the first slide. We were up there, and it was probably that run that you saw back in 1995 or 96. We had this debate, I will never forget it, because it just seems ludicrous at sea level, or even 8,000 feet. It was what's 128 divided by 2. We could not agree. So it's a really interesting place to work. But 14,000 feet, you're above most of the clouds. And in fact, you can look out and see the inter-island flights flying by. This is where this photograph was taken. Is a really interesting place. It's called the Apollo Valley. It's where the early astronaut training happened before they did the first manned missions to the moon, because they thought this would look like the terrain. We've talked about the airflow. So this is just a picture of the world, so you can see where Hawaii is and really appreciate the fact that it's isolated and surrounded by a huge body of water, which really helps this airflow over the mountain, so that's good. This is one of my favorite pictures. It's a montage of the world at night. So you can see the developed parts of the world. And so when you're building these really large telescopes with really advanced technology, you have a very interesting puzzle to solve because you want easy access to advanced technology, high-skilled labor, and yet you want no light or low light levels. So there's very few places in the world that can you'd also like political stability, and you'd like not to worry about people showing up with guns in the middle of the night. And there are lots of stories where that happens. So that's it's funny, but it's not a joke. So Hawaii is a really amazing place. And in fact, there are there's roughly a dozen telescopes up there. And people from all over the world have built facilities up there. So the two things in the almost foreground that look like tennis balls, those are the Keck telescopes. To the right of that is Subaru, which is built by the Japanese. To the left of it, you have a telescope that's a collaboration between France, Canada, and Hawaii. Hawaii's not a country, but sometimes you might think it is. And many other countries build their facilities up here. It's a really amazing place. Okay, so let's come back to the two campaign promises. So the second campaign promise, you want to see a lot of detail. So what's the problem? Why has this been so hard to achieve? And I've spent most of my career working on techniques to overcome the blurring effects of the Earth's atmosphere. And it's actually quite profound. If you think about the atmosphere, the light that we're trying to study at the center of the galaxy has been traveling to us for 26,000 years. I mean, if you think about playing like I don't know if you, United used to play this game halfway to Hawaii, if you'd figure out what the time was. So in my group, we used to play, well, what's halfway to the center of the galaxy? Or sorry, for the light, halfway to Earth. Well, when this light that we're collecting today was halfway here, the first cave paintings were being made in France. I mean, to me, that's rather amazing in terms of the history lesson, or just, I mean, and this is that's short on astronomical time scales. But from the point of view of this atmospheric distortions, this light that's been traveling to us pretty much unperturbed hits the top of the atmosphere in the last 30 microseconds. Okay, so this is they say accidents happen close to home. It's true here in the center of the galaxy. Okay, so this is a picture of the 5 brightest stars at the center of the galaxy. If there were no atmosphere, each of those 5 stars would be rock solid still, and the size of the smallest structures you're seeing dance around. Okay, so they're dancing around because of the atmosphere. There are two analogies I like to make here to help us conceptualize what's going on and how we solve it. So the first is, if we think about trying to observe a pebble at the bottom of a stream, and the stream is moving by rapidly, that motion and all that turbulence in the stream makes it very difficult to get a clean view of the pebble at the bottom of the stream. Okay, so that's exactly what's happening here. We have a turbulent medium, and it's messing everything up on really short time scales. The second picture that I'd like to you to have in your head is that the atmosphere is like a circus funhouse mirror. So if you think about going to look at yourself in the circus funhouse mirror, it makes you look distorted. And we're trying to figure out how to take that distortion out. Okay, so there are a lot of solutions to this problem of the distorting effects of the Earth's atmosphere. One is you get above it, and that has been the very, very, very successful solution of Hubble Space Telescope, and is also the solution of the James Webb Space Telescope, which we just launched Christmas Day and is doing its job, unfurling. We're super excited about that. But I'm going to give you a caveat. Actually, this is probably an unpopular view. It's actually a pretty small telescope from my point of view. So Hubble is 2.4 meters in diameter, and even James Webb is 6 meters. And we've got a 10-meter telescope on the ground, and I'm going to tell you why this is still a great thing. Two things work together very well, but let me explain first. Okay, So the power of overcoming the atmosphere and getting to the theoretical limit in terms of angular resolution, we call this the diffraction limit, goes as the diameter to the 4th power. Okay, so compared to, let's start with Hubble. Hubble to Keck is 2.4 to 10, and because I'm not at 14,000 feet, I can actually do that math. And that is more, if you take that to the 4th power, that is 4 times 4 times 4 times 4, and that gets you more than a factor of 100. Okay, so if you think about anything in your life that you would like more of, and you'd probably work pretty hard if you could get that factor of 100 out. Okay, so that's the background to why work so hard on this. And the technology, it's been amazing over the last 2 decades. I mean, I'm studying the orbits of stars, and definitely time is on your side. I mean, the longer you wait, the more science you can do with these orbits. But the other thing that's happened is the huge advances that have been made in the technology. So one of the things I like to describe the work that we've done is really technology-enabled discovery. So you'll see that what we've been able to do has really changed drastically over the last 25 years. So this just gives you conceptually what's going on. If you don't do any of this business, no matter how you do it, those 5 stars that we were looking at, the bug splat pattern, if you take a long exposure, they just look like a fuzzy blob. And everything blurs together, and you can't see the stars that you really care about. You can't discover them. Okay, so if you turn your system on, and this is the more recent stuff of adaptive optics, where I think the black hole is, and we can get to this later if you guys are interested in why we looked here. There was very good reason to suspect that that was the heart of the galaxy. You can see that it's only by turning the system on that you can see the stars that are at the center of the galaxy, and it's those stars that you want to watch move. All right, now in the beginning, we did something very simple, and it's also one of the things I really appreciate about the Keck Telescope, and it's really one of the advantages of a ground-based telescope. It's really easy to change your instrumentation. Once we launch James Webb, we have launched it, its instrumentation is fixed. It starts with whatever it started with, and it's going to be there for the whole mission. With Keck, you can always give it a facelift or renovate the house by upgrading the instrument. So when I first got to UCLA, what I did was just to modify existing instrument. So it was hardware simple, and therefore cheap, and software hard. We took these quick snapshots and took them back to UCLA and wrote a bunch of code, used supercomputers, and tried to figure out what the atmosphere was doing. So really, this data that I've been showing you is actually the data that we took, and we just had to figure out what was the underlying source and what was the atmosphere doing. Okay. On the right is what we got out of the series of pictures on the left. What I'm going to show you is not cleaned up. There's nothing that's been tuned up for PR purposes. I love looking at this movie. I'll tell you, you know why? Because 1, it tells me that my technology worked. And 2, there were stars to discover. And 3, it wasn't that, and they moved, they hauled. I mean, I just can't, there's something about being told no at the beginning of an experiment that makes it so much more gratifying when it works. You can probably find my favorite star in the universe. Its name is SO2. I have to share with you. I don't think I've ever shared this with the public audience. I moved to LA, and I was driving down Sunset, and there were star maps being sold. I thought, oh, they're really into astronomy here. But no, it's a different kind of star. So this is my favorite star in the universe. Okay. So we did that for a while. That was the early technique. It was hardware simple, software hard. And then there was just a renaissance in the mid-90s because there are other people in the universe who care about looking up and down through the atmosphere who have far more money than the astronomers do. and that's the military. So the military was also working on this technology of figuring out how to beat the atmosphere from a hardware perspective. So as the astronomers were making a lot of progress, it got to the point where the government basically said, we don't need to give you this money. We know how to do this. So it was declassified. So then it just became a case of how do you apply this to the astronomical setting? Okay, so this is an animation of showing how this amazing technology, which is called adaptive optics, works. A couple miracles have already happened. The dome went away. And now we're going to see, so you see the telescope structure and that mirror. So you see the light coming in, bouncing off the primary mirror, the secondary mirror, and going behind the primary mirror. This is often where instruments are kept, but not always. And again, there's going to be some miracles. So we're looking at inside the instrument bay and looking in at the heart of the adaptive optics system. You're going to see two depictions of light. One is how it travels, which is this beam of light. And it's going to bounce off the most important piece of the system, which is the top right. This is the adaptive optics mirror. So remember we talked about that circus funhouse mirror? That's the deformable mirror that's going to try to take on the opposite shape to the shape that the atmosphere put on the, what's known as the wavefront. Okay, so this guy, second circus funhouse mirror, has to keep up with the atmosphere. If there were no atmosphere, these wavefronts would be flat pancakes. Instead, they look like Pringles potato chips. And once you close the feedback loop, and we'll talk about in a second very briefly what it's looking at, now it's doing that. It's wiggling about 1,000 times a second to make those things look like pancakes again. And then you should get a cleaned up picture. It's about to happen. So you go from bug splats to something that's tight. Okay, so that's the underlying, that's how adaptive optics basically works. We use lasers to create artificial stars that we can look at that are bright enough to tell us how to make that deformable system work. And I won't go into that, but there's a lot of really interesting stuff in this component of the system. Okay. So we've been watching how stars move. We've been doing this for 25 years. Okay, so now we're no longer doing just watching how the speeds of things, which remember was the original proposal, just watch how fast things move, and then statistically argue what's at the center of the galaxy. And what I love about the scientific process is that if people aren't convinced, they're gonna push back. They're gonna say, we don't quite believe you. And that means you have to do more, you have to do better. And that really pushed us to do this much harder experiment, which was to watch, to really measure the individual orbits and to continue. So in spite of the fact that they didn't accept a 3-year program, they're now 25 years later still supporting us. So they didn't really understand what they were getting into. Okay, so the yellow star, trailed by a yellow line, is my favorite star, SO2. It goes around every 16 years. I think I'll just leave it at that. Actually, no, I'm not going to leave it, because otherwise you're not going to understand one piece. The beginning technology was all about taking images. Images are super easy to explain, because you get it. You take a picture, there it is, and you can measure how things move on the plane of the sky. Once adaptive optics comes online, you can take spectra, which tells you how things move along along the line of sight, which is the third dimension that's missing. So stars are trailed by a dashed line when you have them in images. So some stars appear not because they're brighter, but rather because your technology is getting better. And then once adaptive optics comes online, we start to be able to get the spectra, which is that third missing dimension. And then the stars are trailed by solid lines. Anyway, so what does SO2 and friends tell us? Well, it tells us that compared to the starting point, which is that we knew there was 4 million times the mass of the sun, contained within this circle, this big circle, which was far too big to claim that there is a supermassive black hole. You're well far away from the Schwarzschild radius. That once these orbits are measured, you've confined that 4 million times the mass of the sun into a region of volume that's 10 million times smaller. In other words, you've advanced the evidence for the existence of supermassive black holes by a factor of 10 million. So that's a huge step forward and has really moved us from the possibility of supermassive black holes to a certainty that these things exist. Oh yeah. And I'm also showing you that the mass now, these 4 million times the mass of the sun, is confined to a region that corresponds to the size of our solar system. So if you think about our solar system, which is really dominated, the mass is dominated by the mass of the sun. So we have 1 times the mass of the sun. Inside that same region, we have 4 million times the mass of the sun. So a lot more mass crammed into that same region of space. Okay, so today we're no longer trying to demonstrate the existence, but today we do have this strong evidence, and that is really the heart and soul of what the Nobel was all about. I really want to highlight, though, that the prize was awarded to 3 people, and the curation of the Nobel Prize is always really interesting to look at. So half of it was awarded to a theorist, and half was awarded to 2 observers. So in the beginning of this lecture, I hope I really communicated the importance and the interplay between theory and observations. And then the second half of the prize was split between a group that's led by, awarded to Reinhard Genzel, who leads a group in Germany. And this group has been competing with my group for the last 25 years. So I just wanted to briefly comment on the importance of competition. So I'm really delighted that, that both groups were recognized, because there's nothing like having a little competition to keep you both on your toes and pushing you to understand very carefully how to make these measurements correctly, because really, they're the only other group that understands in minute detail what you're doing. So there's a really, I think that at the end of the day, 2 competing groups do much better science than either one could alone. So this now shows the animations in 3 dimensions. So I just wanted to mention one thing in terms of what are we doing today. The technology has changed so much that today we've not only been able to answer the question that we set out to address, which is, do supermassive black holes exist? But it's now shown us questions that we didn't even think to ask. And specifically, in our ability now to understand the region or to observe the region around the black hole, we're seeing that almost every prediction we could make for what's around the black hole is inconsistent with the predictions. And from my perspective, this is like job security, or a better description, it's like a kid in the candy shop. There's so much more to understand. I've only recently come to understand that the delight that scientists have when we're confused is not a typical reaction to confusion, because it really says you have more to learn, and it points the way to those understandings. So just to give you a slight understanding of the things that are color-coded in here, the first prediction was that there should be no young stars. This is a very violent region for all sorts of reasons, but primarily because of the black hole. Black hole creates what's known as tidal forces that should tear up anything that's capable of forming these young stars. And what do I mean by young? If you anthropomorphize stars, these young stars are like the human gestation period. So these are really baby stars. And yet, if you look at this picture, they're the dominant part of the population. So I love to call this the paradox of youth. How did you get these young stars? Because your prediction was there shouldn't be any young stars. And in fact, young stars even further out was why people said there couldn't possibly be a black hole at the center of our galaxy. And now we've made the problem even worse. Okay. There's a hint that you might have picked up in that disk of stars. Those young stars seem to have a regularity in how they orbit. Okay, so that's a clue, and it has all sorts of interesting ties to borrowing ideas from how planets are formed. So it's a lot of fun to work on this problem. Another problem is the prediction was about the old stars. Old stars have been around for a long time, should congregate around the most massive object in the system, which is the black hole. The old stars in this thing are color-coded as orange. There's a dearth of old stars. So again, opposite of the prediction. And that prediction is really important in our field because we often use the excess density, the excess of these old stars to find black holes in other galaxies. So again, what's going on? And the third is why I'm here at this conference. So if you'd asked me 10 years ago, is there any connection with the center of the galaxy and gravitational waves, I would have said, no way. But very soon after that, we discovered these really weird objects. They're the pink objects or the magenta objects. And these are objects that are being, where the outer layers are being torn apart. So think giant tidal waves. If you think Interstellar, of that planet with a giant tidal wave of the planet near the black hole, this is extreme versions, like it's just being lifted off. And you see that. These are the, and there's no object that we could predict ahead of time that should have had that kind of interaction with the black hole. So this is lots of fun to think about. And our best idea, and this is work that I've done with Professor Naus, who is up here doing the Science Cafe, is the idea that let's remember that most stars start their life as twins. They're very tightly, closely spaced, and they orbit around each other, and they go around the black hole. And you can get this three-body interaction between the black hole and the little binary, where the black hole drives these guys to merge. And when stars merge, they get really big, and then these interactions can happen. Gravitational waves are all about merging processes. So that's all of a sudden the connection, and it may be an important connection, because in the gravitational wave community, they're seeing stellar mass black holes that are much more massive than they expected, and perhaps merging more frequently. And here we're highlighting a process that may give a hint to some of those ideas. It's kind of late, so I think I'm actually going to leave it there. So if nothing else, I hope I've convinced you that there's a supermassive black hole at the center of our galaxy. This gives us the best evidence to date that we have for the existence of supermassive black hole, and has created a wonderful laboratory for understanding both the physics and astrophysics of black holes. Thanks for your attention. Are we taking questions? Yes. Okay. Sorry, it's really hard to see with the lights. Yes.
Are there any competing theories that would account for whatever data you have about how things are moving around in the center of the galaxy? Is there any competing theory to that there is a black hole?
Oh yeah. So this was really fun. So in the beginning, in the early days, when we just had velocities, the improvement, rather than being a factor of 10 million, was a factor of 1,000. And at that point, the particle physicists got into the act. I think it might have actually been at one of these meetings at the Aspen Center for Physics. And they said, well, let's think about an object that's composed of fermions, only fermions. It would be like an extreme version of neutrons. So neutron stars are objects that are compact. They're formed of only neutrons. And so it would make this object even smaller, but not quite within the event horizon. And so it was only with the orbits that we could actually rule out that scenario. Now, it doesn't mean that there aren't alternatives that may come up, because the other question you could ask me is, how close are you to the event horizon? And then I would have to say, well, actually, we're about 500 times out from the Schwarzschild radius of 4 million times the mass of the sun black hole. So there is wiggle room. It's just no one has come up with an alternative yet. Doesn't mean there isn't. So it's important to keep that in mind. Actually, I'll keep going with this. So if you read the Nobel citation, they were super careful about this. So they said, it's not for the discovery of a supermassive black hole, it's for the discovery of a super compact object at the Galactic Center. So they left themselves some wiggle room. Okay, yes?
From this perspective, where is this thing?
Oh,
No, if I was outside and I want to say the center of the galaxy,
okay.
the black hole, where is it?
Okay, so if you go, the center of the galaxy is best viewed in the summer. So this is another thing that that's worth pointing out. The Galactic Center work that we do is seasonal. It's seasonal work, and that's because if you think about the center of the galaxy being here, this being the sun, and then the Earth going around the sun, you have to do your work at the part of the year where you're on the side, and the sun's on the other side. So when we're over here, which is the winter, so now we're not going to do this. It's only during the summer that we can do this work. So we start in the spring and we go through early fall. If you go out at night in the summer, it's up at the high, it'll be right as high as it's going to get mid-June. And if you, at middle of the night, of course you'll see it at other times, look for the constellation of Sagittarius, which is the teapot constellation, and it pours in to the center of the galaxy. So that's the camping, yeah, exactly, yes.
You still refer to it as Sagittarius A?
Oh yeah, so the black hole has the name of Sagittarius A star, which is the worst name ever, okay, it turns out. So if you look at the center of the galaxy at radio wavelengths, you see an unusual source. And it kind of looks like a very faint version of the active galactic nuclei. So not bright enough to get it, that got people really excited, but it had the same characteristics. So it was like a black hole that was having a snack, maybe. Okay, so that's why we pointed our telescope. Like we said, okay, let's look where Sagittarius star, it happens to be where all the stars, the density of stars also peaks. It's all the same region. So it's the brightest radio source in the constellation of Sagittarius. So Sagittarius A because it was the brightest. And star because the guys doing this had a nuclear physics background and they were trying to be clever. So the idea was asterisk, it's really an asterisk, in nuclear physics means excited state. So they were trying to say, Sag A, not a star. Its emission looks like excited gas. That's why it's the lousy name.
One of the stars was behind the event horizon.
None of these go behind the event horizon.
I imagine there's a bit of distortion
Oh.
because you don't see the object because it's an empty state. It's like going behind the sun or
Right.
an object where
So we haven't yet seen an object go behind it. And what actually happens is super interesting because light usually travels in straight lines, except when it gets near strong gravitation masses, and it'll bend the light. So we get this effect called gravitational lensing. So it'll basically make the stars look not quite where you expected them. It'll actually, what it'll do, I mean, let's pretend you're looking at a star that just moves in a straight line. What it'll do is like a little tent-like pattern as it goes behind or within the region that it can get lensed. So we're actually actively looking for these events to happen. And at some point, if you believe you understand what's at the center of the galaxy, you should be able to capture those events, but we haven't yet. Well, it's another angle on the physics. And so in today, what I skipped over at the end is we're after a couple of different things. Not only on trying to understand all these mysteries about the stars, but we're also after SO2's orbit. We're looking for the precession, which means the orbit doesn't come quite back to the same place. And that's a prediction of Einstein's theory of general relativity. So you should see this, and it would be exciting because this would be the first direct test of how gravity works near a supermassive black hole, so in an unexplored regime. And you only get a seat at the table to do this kind of work once it's gone all the way around, and then it starts to go through the next turning, what I call turning at points, which are the closest and furthest of points. So you have to wait 16 years even to get a seat at the table. And then you can start to do this work. And what's super exciting now is that our early results suggest that things are this star, SO2, is actually precessing in the opposite direction at twice the rate. Again, not what you expect. And again, this is my favorite part of doing science because you have to think very carefully. You have to think about, well, if it's physics, what would it be? But before you get to that, you have to ask, how could I have gone wrong? Like, all the machinery that we've created to do this work is homegrown, pretty much. And there are a whole bunch of assumptions you make. So you have to go carefully through all your assumptions to make sure that it's not just a mistake. And the visual I have there is like it's like going around your car and just kicking all the tires to make sure that there's nothing that might give this to you just because you've made some assumption, simplifying assumption that used to work but really no longer holds. So it's a fun phase. But if you believe the signal, then the interpretation would be the discovery of dark matter around the black hole. And that would be an extraordinary result, but extraordinary claims require extraordinary evidence. So we're really deep into this right now. So it's another interesting phase of the work. Yes?
You seemed a wee bit dismissive of the James Webb Telescope.
Oh, sorry, thank you for bringing that up again.
Any benefit to you?
Yeah, well, so we actually have a couple programs. Oh, the question is, I was a little dismissive of James Webb Space Telescope, and I meant to come back to that. So James Webb has lower angular resolution. So in terms of playing these or doing these experiments really close to the black hole, it's all about resolution. So the larger telescope will always win in this region. The other issue for where one telescope is better than the other is about the density of stars. So the density of stars starts to fall off as you move away from the center of the galaxy. So at some point, it's actually an advantage to use the James Webb Space Telescope, and it gives you a much bigger context. So the other thing that is helpful to point out, adaptive optics works wherever your laser points. And then the corrections it makes fall off really rapidly as you move away from where the laser is. So James Webb gets, in one shot, a clean image over really big spatial scales that we would have no hope of doing with the adaptive optic systems at Keck. So we basically look at the large-scale system, first with Hubble, and now with James Webb, and then do the precision work right by the black hole with Keck. So there's a really nice complementarity between the two. Thanks for asking that. Yes?
You have your competitor with whom you share the Nobel Prize. Do you take time to, and do they take time to vet your work?
Yeah, that's an interesting question. Yeah. Sorry. This is like the human side of science. And quite frankly, I wish I'd kept a diary through this whole process, because I began this project the first year I was an assistant professor. So I was really young, and I didn't understand a lot of things. And so as this has gone along, and I think it's become more and more clear that there was a lot at stake, the way the collaboration, or lack of collaboration, I should say. So I've been a strong proponent at this point in my life for keeping them independent, because I think you learn a lot from having two groups that do things differently, think differently, have different code, and we always in science have the opportunity to check. So the standard in science is that we publish all our results, and at the end of the day, we should be able to check our competitors' work, and we should be able, in our publications, to write down all those steps that go into this. So in a sense, there's a slow checking, but we don't do the pre-checking anymore. I did that once in the beginning of my career, and I got very badly burnt. So what do they say? Fool me once, shame on you. Fool me twice, shame on me. So didn't do that again. Yes?
So you're saying that all black holes have the same volume, but different masses?
Okay, so this is a question about black holes' volume. Okay, so we have to be super careful here, because we don't understand the physical size of black holes. So that's where we get in trouble, because if we take our physics seriously, it says there's no finite size. And that's true for all black holes. Presumably there is some physical scale that comes in, maybe Planck's length or something at the quantum length scale. So I guess in that sense, we are saying at that scale, it looks like they're all the same. They all have this problem, and they have different masses. The Schwarzschild radius for any black hole, actually it's very easy to calculate. If we measure the mass of the black hole in units of mass of the sun, multiply that number times 3, and you get the Schwarzschild radius in kilometers. So it's really just scales with mass. You double the mass, you double this abstract size of the Schwarzschild radius. Does that answer your question? Okay, great. Okay. Up above. Ooh, thank you.
So you observed light being that,
We haven't observed light being bent, no.
I always thought that black holes were sucking up oxygen.
Oh, yes. Okay, so yes, black holes have this bad reputation for being, or even the popular misconception of being the cosmic vacuum cleaner. Turns out you have to get incredibly close to the black hole for matter to fall onto the black hole. And to give you some numbers, in our galaxy, we expect a star to fall in through the event horizon once every 10,000 years. So this is not a frequent occurrence, and gas is more, and it will turn into gas, and then it's the gas that really goes in. We are seeing stars that are losing their outer layers, and that gas will eventually make it in. But the stars, it's kind of a, it's an occasional, not too often occurrence. And we are totally safe from this black hole. Like, if you have any concern, there's none at all. We're, out here halfway out. Things are calm. Okay, great. Thanks for your attention.